Have you ever wondered exactly how your phone instantly recognizes your face? Or, how something like ChatGPT actually understands the incredibly complex nuances of human language? Or even how a self-driving car can detect a pedestrian in real time? Well, the answer to literally all of these questions lies in one of the most powerful, foundational technologies in artificial intelligence today: deep learning.
Welcome to this explainer. I am so thrilled you're here with us because today we are going to completely demystify deep learning. We're going to break down the entire learning process of AI and basically transform what often seems like pure magic into a clear, understandable structure. From raw data all the way to intelligent predictions, you're going to see exactly how the machine actually learns. Okay, let's just quickly glance at our roadmap for today. We've got a highly technical but absolutely fascinating journey ahead. We'll hit the core components, structuring the brain, the first guess, the learning algorithm, the training loop, and finally, the big picture. Section 1, the core components, the building blocks of AI. To really wrap our heads around deep learning, we have to start at the very bottom. Think about the sheer contrast between old and new programming methods. Imagine trying to teach a computer to recognize a cat. Traditional programming? Well, that would require us to manually write thousands of rigid rules. If it has whiskers and if it has 4 legs and pointed ears, then it's a cat. It is incredibly tedious, and honestly, it fails all the time in the real world. But deep learning? Totally different ballgame. It's inspired by the human brain. Instead of painstakingly coding every single rule, we just feed the system large amounts of data, like thousands of cat pictures, and we let the computer organically learn those important patterns all by itself. So how does it process that data? It starts right at the micro level with the artificial neuron. Every single one of these artificial neurons performs an exact 3-step mathematical sequence. First, it receives inputs. But since not all inputs are equally important, it multiplies every input by a numerical value called a weight. Higher weight, higher importance. Simple. Second, the neuron adds all those weighted inputs together, along with a value called a bias, which basically just shifts the decision boundary. Third, the result passes through an activation function. This function strictly decides if the neuron should activate and pass its information forward. Multiply, add, activate. It sounds super simple, right? But millions of these calculating together, that's what creates unparalleled intelligence. Section 2, structuring the brain, neural network architecture. Let's see what happens when we connect millions of these individual neurons into a massive structured network. The crucial thing here is how the architecture is layered. First up, we have the input layer. This just takes in the raw data, literally the pixels of an image or the text of a word. Then that data flows into the hidden layers, and this is where the magic happens. Actually, scratch that, it's not magic, it's math. These layers learn increasingly complex patterns sequentially. The first hidden layer might just detect hard edges. The second combines those edges to find curves. The third combines curves to recognize eyes. And the fourth, a full face. Finally, it hits the output layer, which gives us our final prediction. And by the way, the reason it's called deep learning is entirely because of the sheer depth of these networks, which often contain dozens or even hundreds of these hidden layers. Section 3, the first guess, forward propagation and loss. Now that our architecture is built, let's walk through the life cycle of a prediction. What mechanically happens when we feed a picture of a dog into our brand new network? Well, learning always kicks off with a process called forward propagation. The image of the dog enters the input layer, and then that data absolutely sprints forward through every single hidden layer. Every neuron is rapidly doing its multiply, add, and activate calculations. The data flows relentlessly from start to finish just to make its initial guess. When it hits that final output layer, it spits out probabilities based on its current initial weights. Let's say it tells us there's a 70% chance it's a dog, 20% it's a cat, and 10% it's a horse. So the network confidently predicts dog. But remember, at this stage, it is literally just guessing. We need to objectively measure how accurate that guess really is. And we measure that accuracy using something called a loss function. Think of the loss function as the ultimate report card for our neural network. The network's prediction is strictly compared against the actual correct answer. If the image was a dog and the network predicted dog with high confidence, the loss function yields a tiny error. Great job, network. But if it predicted cat, the loss function returns a massive error. It essentially yells at the network, hey, you performed poorly, your weights are totally wrong, and you need to improve right now. Section 4, the learning algorithm, fixing the mistakes. So how does the computer actually fix its mistakes based on that bad report card?
This brings us to the highly technical but undeniably fascinating core mechanism, backpropagation. Let's slow down for a second. Forward propagation moved data from start to finish, right? Backpropagation does the exact opposite. The network works backwards. The error calculated by the loss function travels in reverse through the layers. The algorithm is basically asking, which specific neurons messed up? Which weights caused this bad prediction and need to be tweaked? It's exactly like a rigorous student reviewing their incorrect test answers and tracing their logic backwards to find the exact moment their calculation went off the rails.
But finding out where the mistake happened is only half the battle. The network also has to figure out exactly how much to change those specific weights. I want you to hold a mental image for a second. Imagine you're standing at the top of a mountain, surrounded by incredibly thick fog. You can't see the bottom of the valley at all. The absolute safest, most logical strategy to get down is to continuously feel the slope with your foot and just take small, calculated downhill steps. This metaphor perfectly explains the heavy mathematics of how the network adjusts its weights.
In our network's case, that mountain is the loss function, and the bottom of the valley, that's the lowest possible error. The method used to get down there is an optimization algorithm known as gradient descent. The algorithm calculates the slope, the gradient, of the error, and it continuously adjusts the network's weights in the specific downhill direction that reduces that loss. By taking thousands of these tiny, mathematically precise steps downhill, each update slightly improves the model, eventually optimizing the weights to give us a highly accurate system.
Section 5. The training loop. Practice makes perfect.
Let's speed things back up. We've seen one cycle of guessing and correcting, but real intelligence requires repetition. Learning doesn't happen from looking at just one single image of a cat. The network has to study the entire dataset repeatedly. In deep learning, one complete pass through all the training data is called an epoch. To actually learn, the model has to process the data through forward propagation, calculate the loss, and backpropagate the errors across many, many epochs. You can literally track the intelligence of the network growing over time. At epoch 1, the weights are mostly random. The network is essentially guessing blindly and making tons of mistakes. By epoch 50, gradient descent has adjusted the weights significantly. Predictions get much better as the middle layers finally start recognizing things like ears and tails. And by epoch 100, the model becomes highly accurate, having truly learned the deep hidden relationships within the data. The absolute end goal of all these epochs is something called generalization. A properly trained model hasn't just memorized one specific photo of a cat. It didn't just memorize a grid of pixels. It has actually mathematically mastered the underlying absolute concept of a cat. This is why a fully trained deep learning model can perfectly recognize a specific cat in unique lighting that it has literally never seen before in its life.
Section 6. The big picture. Applications and challenges.
And now that we've got a solid grasp on the under-the-hood mechanics, the structure, the layers, the optimization, let's zoom out. Why is this fundamentally changing our world? Deep learning is transformative because it completely eliminates manual feature engineering. It learns what's useful straight from the raw data. Because of this, it's the engine behind highly accurate medical diagnosis from X-rays. It's how self-driving cars instantly recognize stop signs. It translates languages on the fly, catches credit card fraud by spotting hidden anomalies, and of course, it's the foundational logic powering incredibly advanced chatbots like ChatGPT. But we do have to acknowledge that this immense power comes with some pretty major technical challenges. Running millions of weights through gradient descent for thousands of epochs, that requires massive datasets. You need insanely high computational power, relying heavily on advanced GPUs. Training times can span weeks or even months for the largest models out there, which inherently leads to massive electricity consumption. These heavy costs are exactly what's driving researchers today to constantly seek out more efficient, explainable AI architectures. So, just to rapidly summarize our entire explainer, the magic of deep learning boils down to this precise sequential loop. Raw data enters the network and does forward propagation to make a guess. The loss function scientifically measures the error of that guess. Backpropagation runs in reverse to find exactly where the mistakes occurred. Gradient descent steps downhill to update and fix those weights. And finally, you repeat this across hundreds of epochs until complex, generalized patterns are fully learned.
Deep learning really is changing everything, from healthcare to scientific discovery. And now that you possess a crystal clear understanding of its technical foundation, how it actually learns from raw data to build real intelligence, you are perfectly positioned to explore even more advanced frontiers. Things like convolutional networks, large language models, and the rapidly expanding world of generative AI. So, with this foundation built, how will you use this knowledge to explore what's next? We'll leave you with that provocative thought. Thank you so much for joining me for this explainer, and keep learning.